Hello, everyone. Today, I'll be discussing our paper on the Augmented Two-Stage Bandit Framework, which proposes the practical approaches to balancing exploration and exploitation in an online ad serving system. Our framework aims to address the exploration-exploitation dilemma, especially on cold start and data sparsity problems, by building upon the traditional Bandit framework, enabling more effective ad selection and improved overall performance.
To give a bit of an overview and background to the context of this problem, our ad auction funnel is based around three, let's say, core steps that move from the upper funnel to the lower funnel, from ad eligibility filtering, where we have many ad candidates being filtered down by things such as targeting and ad eligibility, like more bespoke filters. This moves into ad selection, where we select down to much fewer candidates in order to pass into our final ranking, which creates prediction scores for all ad candidates that then gets used directly in the auction. One other very important note is that the final ranking, or pCTR models, are very computationally expensive and requires significant filtering in order to apply them in an online setting. This is where ad selection comes in and plays a crucial role in filtering, optimizing, and creating a layer of exploration for new ad candidates. In the ad selection phase, one thing that's important to note is that our ad management framework system contains a hierarchy from the ad account and even above levels, ad account being similar to the advertiser level, which can contain or create multiple campaigns, each of which can have multiple ad groups. And within an ad group, there can be multiple ads. In this stage, we have systems set up to select one ad per ad group, and that is for that reason of similarity, but also in order to make sure that we can maintain diversity and explore effectively while exploiting within those ad groups.
So this moves on to our motivation. We have a couple constraints and requirements of the already large-scaled ad serving system. So we do need real-time adaptability for the new ads, as we have new ads coming in every day and every quarter, every month. We also need low latency, and this is within the tens of milliseconds, and low infrastructure overhead for us to be efficiently serving these ads. And then exploration is important, where exploring within a range of some confidence bound is equally important. So all that being said, the Bandit algorithm here is very well suited, where we have an agent which observes an impression with the associated feature vectors. And these feature vectors are here around request context, user level context, as well as ad context. The agent can choose an ad from a set of eligible ads based on the learned policy. And then once the agent observes the click, which is the reward for us in this scenario, we then is generated by the impression. We use that to update the policy, and we repeat and rinse such that we serve the system in real time and update the adaptability. And in terms of limitations of this existing method, we actually come from a world with non-contextual bandits, namely the non-contextual multi-arm bandits, where no contextual information is considered when we choose the action or the ad. So though this may achieve fast conversions, especially for new ads, personalization is limited, where the rewards are not optimal at each feature level. So we're basically saying one ad fits all. With contextual bandits, however, we consider the contextual information when choosing the action, and hence the reward function is of some feature vector. And so we allow more personalization. For instance, the time of day, the device at which the user is requesting, and we achieve higher total rewards and performance overall. This is prone to data sparsity and excessive exploration at the beginning stages of learning. And so in practice, contextual bandit tends to perform worse than multi-arm bandits at the beginning, but catch up over time.
Okay, so given the practical limitations we've seen, we want to develop a methodology that gets the best of the both worlds, where we want to achieve higher total rewards with more personalization in the long run. And in the meantime, we don't want to sacrifice the short-term performance at early stage from excessive exploration. So our proposal is an augmented two-stage bandit framework. The first concept is this two-stage framework. The motivation behind that is in contextual bandit, it assumes that the reward function of each context is independent. However, in reality, and especially in the problem space of ad selection, that assumption may not be true. We can totally imagine that the best performing ad for the overall population can probably perform very well for specific user groups as well, such as iOS users or Android users. So our approach will be this two-stage process, where initially, while the contextual bandit is still learning, we will use this context-free policy to select the overall best performing ad. And once the contextual bandit is well trained and provides better performance, we will switch to this contextual bandit for more personalization. We will determine the transition point based on the variance of the expected contextual reward, which is a measure of the degree of exploration and uncertainty. This variance will be compared to a threshold, and this threshold is a parameter we can tune over time using offline or online testing. The second part is the augmentation. We can consider this as a knowledge distillation from the heavy ranking pCTR. We know that at the heavy ranking or final ranking stage, we have a very sophisticated but very accurate pCTR. But this pCTR is not really feasible to be used at the early ranking stage due to latency and cost. So instead, we will use the previous stage pCTR and incorporate that information to further help with cold start. And this score will be used as a weight for the context-free rewards. So here comes to our final proposal, the augmented two-stage bandit framework. So initially, we'll rely on the augmented context-free policy to address the cold start issues. And then later on, as the contextual bandit becomes more effective, we will transition to rely on that, where we can get more personalization recommendation.
In order to test this hypothesis, we set up some online experimentation. The exact hypothesis that we were testing was that this augmented two-stage bandit framework could produce measurable performance improvements. But we were particularly interested, as mentioned, in solving and improving upon the cold start and data scarce scenarios. The 4 variants that we set up for this experiment include the control-based linear Thompson sampling model. This was the contextual bandit that we use as our base. And then from there, we have combinations of the other implementation. In our results, we found significant lift, but modest lift in CTR from our proposed augmented two-stage bandit. Notably, this was significantly higher than the other 2 treatments, as well as control. One thing that was very exciting was that we did find significant and substantial improvement in those data scarce scenarios. We represented those data scarce scenarios by their percentile of impressions per ad group. This allowed us to understand in ad groups with low impression volumes how much lift were we able to create with this proposed method. And we showed a significant greater than 10% lift in some of those data scarce scenarios while keeping the overall lift greater than control. Finally, as a guardrail, we always look to click volume to make sure that we're improving the overall system for advertisers, and again, found substantial lift in our proposed method. In conclusion, we do find that the two-stage augmented bandit framework provides a set of notable improvements on top of traditional contextual bandit formulations, and very specifically addresses some cold start and data scarce scenarios that we frequently run into. Additionally, we aim to have a practical application for serving in an online environment with low latency requirements. And finally, we were able to back this hypothesis up with online experimentation, showing those key improvements in our click-through rate and particular improvements in those cold start and data scarce scenarios. Thank you so much for taking the time to listen to our talk, and enjoy the rest of AdKDD. Thank you.